Okay, so now that we've looked at both scalar line integrals and scalar surface integrals last lesson, I like to do a little side-by-side comparison to help you see some of the similarities and some of the differences. One of the first things I like to point out is when we're talking about a line integral, we have to think about the dimension of the object. This, if I just have a wire that's sitting here in the XY plane, I consider this a one-dimensional object that's sitting in 2D space. And the reason I'm calling it one-dimensional is technically we can parameterize this curve using just one variable, s or t, whatever we'd like, but I could describe exactly where I am on that curve just using one variable. And similarly, this would be still a 1D object in 3D space. And the dimension of the object is going to be important because that's going to help tell you what type of integral you need to use. One-dimensional object is going to require a single type of integral, which is what we define as a line integral in this case. As opposed to our surface integral over here, where this surface is actually what we'd call a 2D object, and this is sitting in 3D space. And it's a two-dimensional object because technically the minimum number of parameters that you would need to describe exactly where you are at a point on this surface is 2. And we can do that actually by parameterizing the surface, which is out of the scope of this class. But I think you can picture, you can see roughly there's one dimension that way and one dimension that way where you could describe where you are. So if you're trying to find out some information about a 2D object, for example, its mass or its average temperature or its area, that's going to require a 2 or a double integral because of the 2 dimensions involved when you add up things over that region. Okay. Now, I also like to picture what it means if we just add up ds. And what's hard or confusing a lot of times about our notation here is we're going to use lowercase and uppercase s to mean different things, and it's sometimes really hard to tell what we're writing. So lowercase s is going to be associated with just this single integral because lowercase s has to do with arc length along the curve. And in fact, if we chop it up into little pieces, these are length delta s. So if I just am adding up, imagine that your f right here is just 1. It means I'm just adding up all these lengths, delta s. As I chop it up into more and more, I'm still going to end up with just the total length of the curve when I take that limit. Similarly over here with surface area, this d capital S, what we mean by capital S is, let's sketch this in here. So one of these areas is delta capital S. And so now I'm adding up an area everywhere over my region, and that's why when I take that limit, and again, my f here is just 1, so I'm just adding up these areas, take the limit, I'm going to get the total surface area. Now, this is important also because if I want to know the mass of these objects, then the density I give you needs to reflect the dimension of the object. So notice the density, if I'm asking for the mass of a wire, is going to be mass per unit length because my object is really one-dimensional in the sense of only needing one parameter. Mass of a surface is going to be, density is going to be given in mass per unit area, which is going to be a hint again. If it's in mass per unit area, we're going to need double integrals. Okay, so the mass formulas, they'll look very similar. It's just what type of integral we use, which is coming from what type of object we're trying to chop up. Similarly, center of mass formulas are going to look very similar. It's just what type of integral we're using. Now there's one piece that we haven't talked about at all with scalar line integrals that actually doesn't have a nice analogy with scalar surface integrals. And I'm going to show you a visual here. Okay, so here we are imagining that this is my curve C that I'm going to be integrating over, and I'm chopping it up into a bunch of little pieces of width, delta S, which is reflected by here. And then I'm multiplying those little widths times f of xy. And I can picture that as a height of a mountain. So here, let's suppose that this red mountain here is the function f of xy. And so at any given point along the curve, I'm taking this width, delta s, times this height, which is coming from my function. And that's going to be giving me the area of this little subrectangle, or this rectangle right here. And I'm adding them up and taking the limit, right? That's what's really happening with this integral notation. And as I chop this up into more and more pieces, I'm going to be getting a much more accurate calculation of this area of this windy fence. And so that's one way we can picture what a line integral of a scalar function is representing. It's giving us an area just of this little windy piece here that is sitting right on top of my curve. Now this is the part that I was pointing out doesn't have an analog when it comes to scalar surface integrals, because if I'm integrating over a surface that is sitting in 3D, then I will have some integrand that's a function of x, y, and z. And I don't have any way that I can visualize this function of 3 variables, because I would need 4 dimensions. So the unique piece, the reason I'm able to visualize over here in the line integral case, was only when I'm integrating over a curve in the xy plane, where my function is just a function of 2 variables. If I had switched over here to integrate over, say, a helix in 3D, my integrand would now be a function of 3 variables, and I would have no analogy or no way to visualize my line integral. So this one over here, f of x, y, z, d little s, we have no way to visualize that either. Okay. Now we can also define average value of my function over a curve, similar to what we did with surfaces, that it's just given by the integral of the function along the curve and then divided by, now your denominator here is going to represent arc length, whereas opposed to your denominator over here is representing your surface area. All right, and then let's talk about how these are similar and somewhat different also in how you evaluate them. So we see in both cases to evaluate, we're doing some type of change of variables. So with this scalar line integral, I'm parameterizing and then I'm changing ds. So let's parameterizing, I'm putting everything in terms of t, usually that's part of my change of variables, and then I need to change my ds to be in terms of something involving t and dt. And we found that since ds is a tiny little distance, the equivalent analogy is to rewrite that as your speed times your time, or your rate times your time. Okay. Now with surface integrals, we also do a change of variables of sorts. What we do is we have our integrand in terms of all 3 variables, and we decide 2 of those 3 that we're going to rewrite everything in terms of. And that's basically the plane we decide to project onto. And so if, in this case, I'm just going to rewrite it assuming we were just going to project onto the xy plane. So my integrand then stays in terms of x and y, but then I rewrite z in terms of x and y using what I know about the surface z that I'm confined to, where I'm integrating over. And then my ds, we showed last time visually that that little patch of area on the surface is actually equivalent to the magnitude of the gradient of a vector that's normal, or excuse me, the magnitude of the gradient of g, where we're thinking of this surface here as one level surface of a function of 3 variables. Okay, so we're going to take the magnitude of the gradient divided by the absolute value of the dot product between the gradient and a vector that is normal to the plane where you are projecting. And if this all looks very foreign, then go back to the last lesson's videos because we derived visually exactly where this comes from. And in both cases, these little pieces here are considered the Jacobian of these change of variables. We found that both of these we're finding more geometrically instead of using the Jacobian formula, like we did with spherical and cylindrical coordinates, but it's the equivalent concept in terms of what we're doing with the integral.